Building off of 7.1, where we looked at kinematics of rotational form, we now segue into Newton's laws of rotational form, the topic of 7.2. So first thing we need to start off with is defining the rotational analog of mass, what we call the moment of inertia. So the rotational analog of mass is called the rotational inertia I of an object, or the moment of inertia of an object, which we represent with the letter I. It depends on two primary factors: the mass m of our object and the distance r from the axis rotation of our mass, which describes the distribution of the mass from the center. So as we see right here, we have our mass is located a distance r from the center, okay? So that's going to predominantly determine our moment of inertia, okay? The more mass is distributed, the larger the distance, and hence the larger the moment of inertia. The less the mass is distributed, aka the closer our mass is to our axis of rotation, okay? The smaller the distance and the less distribution there is, and thus the smaller moment of inertia there is, okay? So for a point-like object, say if we have a mass m that is located a distance r from an axis of rotation, so a point-like object like this, the moment of inertia is going to be defined by the equation mi equals mr squared. So again, this equation right here captures the fact that as distance of our object grows, the moment of inertia will grow, and as the mass of our object grows, so too will the moment of inertia. If you're wondering a little bit more about how we get moment of inertia and how we calculate for various objects, and how the concept arises, that requires us to go a little bit more of calculus. So we won't go into calculus, but we will explore the concept of moment of inertia a little bit more in class, because it can be a very tricky concept to wrap our heads around. So the units for the moment of inertia are kilograms per meter squared, kilograms being the unit for mass, and then meters being the unit for our distance r. Okay, so we get kilograms per meter, or kilograms meter squared, not kilograms per meter squared. So torque. Torque is represented by the Greek letter tau, fancy looking T right here, is a rotational analog of force and depends on the following factors: the distance r at which the force acts from the axis of rotation, the applied force F, the angle between the force vector F, the end of the vector, not the tip, and the distance r. So right here, to illustrate, the torque is going to depend on the distance r at which our force acts, the amount of force that we apply, and then the angle between the force vector, the end of our vector, okay, so the tail, and the distance r right here. Okay, so here's our distance r, here's the tail of our vector, so this gives us our angle theta right here, okay? The equation for torque is represented by the equation torque equals F force times radius times sine of theta, okay? This equation, again, comes from a little bit of calculus, specifically a field of calculus known as vector calculus. But there are many ways to demonstrate and visualize torque, some which will be covered here, and then other ways which will be covered in class in order to better help you visualize, okay? So the units for torque are force times distance. Since we're going to have force times distance right here, force times F times R, which gives us newtons times meters, or Newton meters. So that's our equation, that's our unit for torque, okay? So in order to imagine the concepts at play here with torque, okay? Imagine if I was to apply this force, if we're trying to get this bar to rotate right here. If I were to apply this force F right at the axis of rotation, so R equals 0, we would not be able to get our door to rotate, like if you're trying to push a door with the hinges. But the further away you move the door, or the further away you push and apply your force F, the easier it is to move the door, and that's because you're increasing the distance R at which your force acts, and thus you're increasing the torque. Since as R goes up, torque will also increase, okay? Now for sine of theta, okay, you can imagine that if theta was 0 degrees, that means you'd be applying your force along the radius, which means you'd be like pushing into your door or pushing out away from your door, in which case you're not going to get your object to rotate. You're going to be pushing your door into or out of the hinges, which is not going to cause rotation. So we'll look at this a little bit closer with some further in-class demonstrations in class. So this brings up an interesting point now that we've talked a little bit about Newton's second law, or about torque, is we can now use torque to distinguish between rolling and slipping. So if a body is not rolling, say like we have a tire that's at rest, an external torque will need to act on the system in order to induce rotation. So like Newton's first law, an object at rest will remain at rest. The rotational analog of that is an object will not rotate, or it will maintain a constant rotation unless an external torque acts. So if a body is at rest and we want it to rotate, we'll need an external torque to act. Just the same way as a body is at rest and we want it to move, in translational motion, we'll need to apply a net force or an external force. So on a surface, the force responsible for enacting this torque is friction. So if we have a tire that is rolling on a surface, the reason why it's rolling is friction, okay? In order to illustrate this, let's consider a tire that is rotating on two different surfaces, asphalt and ice, with a clockwise angular velocity, so rotating in the clockwise direction, okay? On asphalt, the attempted clockwise motion, meaning our tire is going to try to rotate this way, which means it's going to apply a frictional force on the ground to the left, okay? So as a result, our tire, as a result of trying to rotate in the clockwise direction, it's going to push on the ground and exert a frictional force to the left on the ground. All right. However, the ground or asphalt in this case, as a result, is also going to apply a frictional force as a result of Newton's third law. However, the frictional force in this case is going to go to the right. Again, Newton's third law, equal and opposite forces, and also this friction is going to try to attempt to slow down the motion of our object, impede the motion of our tire. So as a result of this frictional force acting to the right on our tire from the asphalt, this frictional force will cause a torque which allows the car to proceed to the right. Okay? Such a case is called rolling without slipping. So here this force F is from the tire on the ground, which acts to the left as the tire tries to rotate in clockwise direction. As a result, the ground is going to push to the right with a frictional force on the tire, and that applied force on the tire and on the car is what causes the car ultimately to move to the right. This is what we call rolling without slipping. Now there's a little bit more to the story than this, so even myself, I would go, ooh man, I'm still leaving some details out. But that requires a little bit more detail than we're going into for this class here, okay? So on the other hand, if we have ice or other slick surfaces, the friction may not be present or strong enough to enact a torque for the car wheels to move aside from rotating in place. So if you've ever noticed a car that's trying to drive on a really slippery surface, the wheels may rotate, but the car may not move very much. So what we call this is rolling with slipping. Because we're slipping, we're not able to move from one spot to another, so we're slipping in place. The tires are able to rotate, and able to roll, but we're not able to move from one spot to another, so we're slipping. So this is called rolling with slipping here. Okay. So if you have rolling without slipping, friction is acting, and if you have rolling with slipping, no friction is acting. So Newton's second law in rotational form. Newton's second law in rotational form is very similar to Newton's second law for a translational form. Namely, the same way that the translational form says that the net force acting on a system is equal to mass times acceleration, the translational form says that the net torque, the analog of net force, is equal to the moment of inertia I times the angular acceleration A, alpha. So the problem-solving process is the same as before, except now we're going to draw our free body diagram with forces drawn at the point of contact, meaning where the forces now act instead of just at one single point. And then we're going to use the forces to write down the individual torques and sum the torques together. And lastly, we'll solve for an unknown quantity, whether that's angular acceleration or a specific force, just as we've done with Newton's second law in translational form. So let's take a look at Newton's second law for rotational motion. A wheel is rolling without slipping on a road in the clockwise direction where a frictional force of A newtons is acting on the edge of the wheel. If the wheel has a radius of 0.5 meters and a mass of 40 kilograms, what is the angular acceleration of the wheel? The moment of inertia for a disk is I equals mr squared. Okay? So we start out by drawing our free body diagram. All right, again, this first step, we have a clockwise motion. This isn't a force, so we technically we're not going to draw this as a force. I'm just using this to visualize the motion, okay? So in this scenario, we're going to have three forces acting. We have the ubiquitous force due to gravity, which always acts at the center of our object, the center of mass of our object. We have the contact force, the normal force, which in this case, the normal force we're actually going to draw between the wheel surface and the asphalt. Since a normal force is a contact force, it's going to act at the interface between these two surfaces. And then lastly, we're going to draw the frictional force acting to the right. Again, because that frictional force, as a result of our object rotating in the clockwise direction, the frictional force from the road is going to push to the right on our object. So we have that the frictional force is equal to 80 newtons. So in the second case now, we're now going to sum all our torques together. So in this case, we have the torque due to friction, all right, which we're going to calculate here. That's going to be equal to the force due to friction times our radius of our tire, since the force due to friction acts at the radius, times the sine of 90 degrees, which is going to be 80 newtons times 0.5 times 1, or 40 newton meters. Okay? And then we calculate the torque due to gravity. The torque due to gravity is going to be equal to the force due to gravity times r times the sine of 0 degrees. The sine of 0 degrees being because our force due to gravity acts along the radius, so the angle between our force due to gravity and the radius is 0 degrees. So we're going to have 40 degrees times 10 meters squared times 0, and then times 0 again. The two zeros pop up here because our distance that our force acts from the axis of rotation is 0. And we have 0 right here because the sine of 0 degrees is 0. So the torque due to gravity in this case is 0 newtons per meter because the force due to gravity acts at our axis of rotation and acts along our axis of rotation. Lastly, we calculate the torque due to normal force. So calculating the torque due to normal force is going to be normal force times our rate times the distance at which it acts, which in this case is r, since the normal force acts at the point of contact. So it acts at the radial point, better said. It acts at the radius from our axis of rotation. Okay, so we're going to have normal force times our radius right here times the sine 90 degrees. So that's going to be 40 kilograms times 10 meters per second squared, because the normal force in this case counteracts the force of gravity, times 0.5 meters times the sine 90 degrees, which is just 0. So the normal force, in addition to the gravitational force, both enact a torque of 0 Newton meters. So now we can sum our torques together. So we're going to have the normal force torque and the torque due to the force due to gravity are both 0. And then we have the torque due to frictional force, which is equal to which is now going to be equal to our moment of inertia times angular acceleration. So we can plug our equation in for for moment of inertia, which is 1/2 mr squared, and I believe in a typo here, I said it was I equals mr squared. All right, I can't recall which one it is off the top of my head, but either way, you will always be given an equation for moment of inertia. So now we can solve this equation for angular acceleration by multiplying both sides by 2 and then dividing by mr squared, and then plugging in all of our knowns allows us to solve for our angular acceleration. So our angular acceleration is going to be 8 radians per second squared. So we're going to have a counterclockwise angular acceleration in this case because, again, recall positive refers to counterclockwise motion. This might seem a little bit counterintuitive at first, okay? But friction always acts to slow down and impedes the motion of our object. So if our wheels are rotating clockwise in this case, friction is going to attempt to bring our wheels to a stop, meaning it's going to attempt to stop the rotation of our tires. So if we take our foot off the accelerometer of a car, what we'll notice is the car will ultimately slow down, it'll come to a stop, and the wheels will stop rotating. And that's because friction is exacting a counterclockwise torque as your object slows down. Okay? The only reason that this doesn't happen when you're driving is because you keep your foot on the accelerometer, which applies a constant torque in the form of the axle going through the wheels. And this right here is an example problem for Newton's second law for rotational motion.